Hi, this is Andre, back after a long time with a quick update on some piece of software that I updated recently. So let's have some 8-bit times. So today I'm going to talk about the new Commodore Emulator program. Now, why do we need a new emulator? You might ask. We already have Vice, and who know me probably know that I have been working on Vice for a while, quite a long time ago now, and I've been using Vice to run GeckOS on my self-built computer, where I actually built a version of Vice that emulates the hardware for my self-built machine. And I've also been using Vice to capture traces, IEEE 488 traces for the communication between the pad and various disk drives to improve the emulation of my XT2031 firmware for small devices that you can use as a disk drive for a real pad. However, the development speed of Vice has increased, which is a good thing, a very good thing actually. But I found out that they have made some changes that I have not been able to keep up with. So I wasn't able to update my emulator. It's called xcsa for my self-built Caspar and computer with an MMU to the new Vice model. And I'm also not able to capture any traces anymore for the disk drive communication. So I decided to pull out my old xcbm emulator, which is terminal based, which you can see here, that I actually started before I joined the Vice team back in the days. And I ramped it up, and that's what I'm going to talk about today. So what did I do? I updated the emulator, and it's still in the name xcbm. I put it on Git. So you can see, actually there's lots of stuff there, but it you can see it on all the code is on GitHub. You can download it and build it yourself. Then we have now 3 binaries that are being produced: xcbm64, xcbm8032, and xcsa. So xcsa is the version for my self-built computer, and the other ones, of course, are for the PET 8032 and for the Commodore 64. So let's explore a little bit, and we'll start with the xcbm 8032. The others are not that much different. So let's see, what options do you have? You can have trace mode. You can have a control character to enter pause config mode. The point here is it's running in a console. You only have limited ways of interacting with the machine, especially because it's all going over a terminal. Basically, you should be able to run it over a serial line, and therefore you have to put in some kind of escape character, and that's what's being set here. You can load label files that you can that are being shown in the monitor. So all the addresses in the disassembly will then be annotated with the respective addresses from the label file, and then the rest is basically, for now, that's just the ROMs that you need to do. So when we start one of those, so this is basic 4, like you know it from the pad, and it's everything is working as you would expect. But now the question is, how do you get into some kind of more debugging mode, or what features does it have. So there's two ways. You can see here in the bottom line, the escape is Control P. That's the default for the escape character. You go to the emulator stop. Basically, you can remember that yourself as a kind of pause mode, and then you can press Control P again to resume. But you can also press Help, and then you get the commands that you are able to, or the keys that you can press to get actually into those into the next mode. For example, here you can toggle the trace mode. Now you can see suddenly, oh, it's writing out a lot of stuff into the log file, and you see the speed has dropped from 10 times to 43% only. So let's toggle that back. But you can also enter the monitor. The monitor currently is very, very limited. It only has memory and, well, you can actually show it, memory and disassembly commands, and it has a bank command. So if you go and show all your banks, you have in the pet you have two banks. One is the bank that has all the memory, and the other one is what the CPU sees. That becomes more important later when we go to my self-built computer, where we actually have a memory management unit where those two can differ significantly. So, but the only difference here is because what you see here, you have the main CPU. So you see it's prepared for more CPUs, like at some point I may be adding a drive emulation, and the CPU bank. And you can look at the I/O area, and you can see that the you can identify the I/O chips that are here. So and then when I go to the other bank, you can see this is just what's in the ROM underneath the I/O area. Oh my, it's late. What you see here is, of course, what's underneath the I/O area in the ROM. And of course you have the disassembly here. So that's basically it. You can go back to the emulator, and it has already helped me quite a lot to show you something on the next part. So in this part we're looking at the Commodore 64 emulator. So let's start it. And what you can see here, of course, it has color, but I haven't been able to match the colors from the cursors from the terminal emulation with the Commodore 64 colors correctly. So this is green on blue, but well, whatever. There is one difference, but you can see here you can do something with the disk drive, which is only the file system right now. And while the Commodore PET emulator is actually emulating the IEEE 488 hardware, a feature that I built into Vice, and I've taken over into xcbm as well. In the Commodore 64 emulation, I'm using ROM traps to catch the execution of the IEC serial bus, because that's quite a lot of effort to implement it. Also, the keyboard is not yet done with hardware emulation, but with traps. So that means that I cannot run any other operating system on that C64 emulator because, of course, the traps won't work and the hardware is not emulated, so the other operating system cannot use it. But I'll eventually get there. Another feature is you don't need to use Control P. You can also use Control C to get into the monitor directly. There you can see you have a lot of banks, like you would expect from Commodore 64. Yeah, that concludes it with the Commodore 64. The last emulator I want to talk about is the xcsa emulator, which is the emulator for my self-built computer system. And when you start it like that, it looks like a Commodore PET, which is right because it started out as a Commodore PET replica. So, but it actually has a 1 megabyte address space. And how is this used in this machine? This machine has a memory management unit. So if you look at the in the monitor at these addresses here, you see at EFF0 there are 16 registers that are being used by the MMU. And what does it do? The MMU takes the 64K of address space for the CPU, breaks it down into 16 pages of 4 kilobyte each, and for each of those 16 pages you can select where to put it into the 1 megabyte of physical address space. So how is the physical address space used in my machine and also in this emulator? There is one board that has 32K of ROM and 512K of RAM on it, and the 512K of RAM is the upper half of the megabyte bus address space, and also the lowest 32K of this RAM is also mapped into the bottom at address 0 of the physical address space. And then there's 32K of RAM, 32K of ROM, and then I have another board that's 64K of RAM with and this is being used for the video output. And yeah, and that's basically it. So you can see that here. This is basically a 1-to-1 mapping to the lowest 64K in the bus address space, except for this page, which is going to the second 64K, which is the video RAM. So when I patch the boot sequence of the Commodore PET ROM to actually initialize the MMU at the very beginning of the boot process to that setting. So, and the purpose I wanted to have that emulator for is that I wanted to run my self-built GeckOS operating system, which is running in version 1.3 right now on this hardware. Version 2.0 is not yet working, and one of the reasons I did this emulator is to be able to debug version 2.0 why it's not yet running on the actual hardware. So what I can show version 1.3 here. So let's load it. Takes a while. Now we can start it, and you can see, okay, this is a shell where you can enter commands. And you can see here you have devices, video 1 to 4, parallel port, null device, spooler, serial port. Parallel port, serial port are not implemented in the emulator. But anyway, you get the point. You can actually see here what's in the ROM. Oops. Okay. I should have checked that before. So let's start again. What should have been there was a list of those programs that are actually in the main memory, in the ROM area. So, but anyway, I think I know what has gone wrong, but I'll leave it at that. So, and drive C is then the actual IEEE 488 disk drive with the unit 8. So what you can see here is those are the programs that are running. So we have the device file system, which is providing drives A and B. This is the IEC or IEEE 488 file system that provides drive C and D. And on the actual hardware, it's even possible that this machine is being used as a disk drive from, say, for example, another PET, because the code for the FSIC file system also has the kind of disk drive emulation included. And then there's a shell and there's a monitor. So we are here in the shell, as you can see. This is shell. How can we switch? Let's press the add key. And on the add key, you switch between the video console and there's the second video console. And what you can see here is in the memory mapping, you can see here this is different memory mapping than what we had before. So this is the area where the boot ROM for the GeckOS is being loaded into. It's the upper half of the video bank, the upper half of the second 64K. And this is the one page of RAM that is available to this monitor. So it has its own 0 page, it has its own stack. And this is not used, this is not provided. This is actually ROM space. You can't change anything in it. Yeah. So and when I go back to the original, to the first one, I switch to the monitor. And I can look at the same mapping again. And here what I see, this is a different one. This is different. As you can see here when I switch it. Memory page. So we have two processes, two monitors are running at the very same time. And and each one of those has the same, has their own 0 page and their own stack, their own basically memory that they need. This is how this operating system started before I actually managed to port it to machines that do not have an MMU, like the Commodore 64 or the PET itself. So the major objective of this emulator has been reached. I can now run my multitasking operating system on this emulator in version 1.3, GeckOS 1.3, and this gives me the opportunity to actually debug why GeckOS 2.0 is not yet working there. So I hope you like this small, little bit text-centric version of this episode. But I wanted to show you just the updates that I made. And of course, one of the objectives of the xcbm emulator is that I'm going to also implement a micropet emulator in there as well, so that I'm being able to port GeckOS to the micropet and have it run there as well without having to emulate it on the actual hardware, which can be quite tedious if stuff doesn't work. For the next episode, I have to see if I can give an update on the XD 2031 firmware, because I'm currently working on compiling that on a Windows machine, and so that Windows users can also use that Windows machine as a server for the Commodore PET and C64 machines. And also I'm gonna have an update on, I hope, on the Ultra PET Ultra CPU board. So stay tuned and see you next time. Thank you.